Welcome everyone. Thank you very much for tuning into my talk. And as mentioned, my name is Dominik Krzeminski. I'm a PhD student at Cardiff Uni. But before my academia days, I was actually working in industry for tech companies, both like bigger players and some startups. And this is where I got interested more into coding, in particular in scripting languages like Python, R, Julia. And ever since, I was also contributing to open source. So speaking of which, like recently, I'm probably the most proud of my To-Do-R package, which is an extension to RStudio editor. Recently, it was even featured on RStudio Twitter, but you can find my commits also in some other packages, both in Python, like scikit-learn, or R packages that are on CRAN, usually related to Shiny. I try to be quite active in local coding communities like PyData, Cardiff, or Cardiff R users. With this last group, we used to organize annual UK-wide R conference called Saturday. But I came today to actually tell you some story. And the story goes like this, that at the beginning of my PhD, I was reading this paper. And don't get me wrong, this paper is like excellent piece of research, but unfortunately, it was not accompanied with like any code. But the authors proposed the model that I wanted to use for my own research. And I like re-implemented that model in Python. I copied the parameters from the article, but I couldn't quite reproduce the figure on the left-hand side. So I found another paper published by the same authors where they claimed to be using exactly the same model, but the parameters were slightly different. I checked the new parameters, but again, I couldn't quite reproduce this figure on the left. So I moved on to yet another paper published almost like 8 years after, and I got in touch with the authors of this study, and they helped me out actually to solve this parameters conundrum. And I was able to actually implement everything in Jupyter Notebook and reproduce this figure, as you can see here. And this is where I see the future of scientific coding, which is like a closer integration of software and scientific results. And that story could end here, but there's a big but. So I believe that we are actually quite lucky that we live in times where more and more code is actually available online, but the quality of that code is, let's say, questionable. And not to point fingers on like anyone else, actually here on the right-hand side, you have piece of code that I published myself 3 years ago, together with my paper. And frankly speaking, right now, even to me, some lines of that code are quite mysterious. There's even more problems. There's like outdated dependencies that could be solved with Docker, but this is whole another topic. There's lack of README that could help you to get started. The code is not readable, and there's like hidden assumptions that are understood only by the authors of that code. And I listed like many different problems here. And obviously there is no one ultimate solution, but I strongly believe that the step toward in like a right direction is associated with one quite popular recently word, which is testing. And I mentioned you that I have some experience in industry. And back then, when we were pushing some code to production, we were actually testing every little thing. So if user like presses the button, the shades of that button changes from like white to black, we were testing even that. And we as scientists, you probably agree with me, are dealing with way more important matters. And yet still we are not really testing our code. And when I ask my friends, researchers, why they tend to not test their code, this is the typical answers I got. So this is like single usage code. It worked for me the last time, so it's sort of tested. There is aspect of lack of time, and there is also a lack of knowledge. So I'm hoping to address some of that issues with my talk. But before, I want to disclaim that I know that we are scientists, not really trained software engineers, but still it shouldn't be really an excuse from using good practices, especially that the tools are out there. So here I listed packages or modules for the most popular programming languages used, at least in my field, which is neuroscience. I bolded the ones that I'm using myself. But here for the rest of this talk, I would like to present you a little example using this module called PyTest. So let's have a look at this short code snippet. And my question for you is, could you tell me, just by staring like 10 seconds at this code, what it actually does? So I believe that even for like trained Python coder, this is quite difficult task in such a short amount of time. Furthermore, this code is not tested. So I want to test that using paradigm, which is called unit testing. And the idea of this paradigm is that this is a software method that tests every separate chunk of code or unit of code independently. So first of all, we need to actually split our code into those like separate chunks. So let's ignore the first line for a while, as this is just loading a data, and let's focus on the next two lines. So I extract them into separate function that I called outliers. If I'm fancy, I can add some documentation here, but the most important is that this function takes some parameters, it makes some operations on them, and it returns some value in the end. So now I want to verify if that returned value meets my expectations. So how can I do it with PyTest? So in PyTest, typically we create a separate script which starts with test underscore prefix. And inside that script, we add a bunch of functions that usually start with test prefix, which is followed by the name of the function that we actually want to test. And at the end of that function, we have some assert statements. So those statements actually verify if my expectations about the outcome of that function is true or false. So here, for instance, for that function, I can create some fake data, which is matrix, in that case, full of ones, 50 by 50. I introduce to that matrix some like big values, both positive and negative. And then I apply my remove outliers function. And that function, as I can read from the documentation, promises me to truncate the values from negative to positive 100. So my first assertion tests exactly that. If all the values lie in the range from minus 100 to plus 100. Another thing that this function promises is that it not only removes the outliers, but it also replaces them by 0. So since I introduced my outlier in specific place at the location 0, 0, I can test if after applying that function, the value here will be exactly 0. So after writing tests like this, I can move on to my console. I can type PyTest and hit enter. And if I'm in the catalog where my test script is, PyTest will detect automatically all the tests, evaluate them, and report the results in a similar manner. Okay, so now we can move on to the next part of my ugly code. And this part of code is supposed to remove the average from every row of my data. So again, I can extract that line into and wrap it into the function. This time the documentation is shorter for the brevity to put it on the slide. But again, the idea is the same. Now I can test this like separate unit of code. So this time I do it in the following way, that if I define a matrix that is full of zeros, and I introduce to the third row of that matrix some intercept or bias, if you will, 10, and I can compute the average of every row of my matrix X and check if it is close to 0. So in that case, the answer would be no, as you probably can guess. So if I run my tests again, PyTest will evaluate all the tests that I implemented so far, and it will report all the tests that fail in like a neat way, such that I can easily navigate and fix all the issues. But this test failed because we have not applied the mean function that I defined before. So the only thing I modify in that test is that I actually apply that function to my artificial data X. And now, as you can guess, if I run this test, all the tests are run successfully. Okay, but let's come back and see actually how my code looks after all those modifications. So first of all, I splitted my code into like separate functions. So at the end, what I actually have is the structure like this that I'm calling all those functions like one by one. So now I believe that even for non-trained Python coder, it's very easy to tell me what that code is doing. Namely, I'm loading the data, I remove the outliers, and then I remove the mean. Okay, so this is cool, but one could say that such a process is quite boring, right? Writing the code, writing the test, and then running the test in a loop. And I can agree with that, but this is why people came up with something that is called continuous integration. I don't really want to go into too much details. I will just highlight some tools like Travis or GitHub Actions. You can Google them out, but basically the idea is that once you set up continuous integration, you can push your code to some remote repository like GitHub, and all the tests will be run for you. You can even set up some email notifications such that you will get an email when some test fails. Another argument is actually that debugging is even more boring / frustrating, so the tests are indeed an investment for the future. Okay, and towards the end of my talk, I would like to share a couple of like hints with you. So I encourage you to test not only your code, but also your data for all the missing columns, missing values, format of the data that will spare you so much troubles in the future. You should also test assumptions about the function input. Very often we use those scripting languages like Python, MATLAB, and they use duck typing for recognizing the type of your argument, which leads to the situation garbage in, garbage out without any error in the middle. So it's important to test at least like the basic assumptions about the function input. It's a good practice to write rather small functions and perform unit tests rather than testing like 300 lines of code. It's just much easier with debugging. And another good practice is using like a small mock data, as I did in my previous demo, rather than using the actual data for the sake of the performance of the test. And also, if you still encounter some bug in your code, it's a good practice to actually write some tests around that bug immediately, such that it spares you some troubles in the future. Okay, so to conclude, I think that we don't emphasize enough an importance of scientific code testing, as I think that writing tests helps not only you as author of the code to catch the bugs and eliminate them, but also to the community because this code becomes of a better quality. So thank you very much for your attention. At the bottom of the slide, you have my online presence if you'd like to connect and discuss more about that. And now I would be more than happy to answer your questions. Thank you very much again.